All right, today we're pulling back the curtain on the hidden genius that powers our digital world. We're talking about the design and analysis of algorithms. Honestly, it's the secret sauce that makes so much of our technology feel like pure magic.
I mean, think about it for a second. You type pretty much anything into a search bar, hit enter, and boom. In less than a blink of an eye, you get an answer pulled from, what, trillions of web pages? How on earth is that even possible?
You know, the obvious answer is just, oh, computers are faster now. But that's not the whole story, not even close. You could have the most powerful supercomputer in the world, but if you give it bad instructions, it'll still grind to a halt. The real magic isn't in the speed of the machine, it's in the quality of the instructions. It's all about efficiency.
Okay, so let's start there. To really get what efficiency means, we first have to agree on what an algorithm actually is. And the simplest way to think about it, it's basically just a recipe, but a recipe for a computer.
So here's the more formal definition. A few words here are absolutely crucial: finite, clear, and unambiguous. You see, a cooking recipe might say something vague like add a pinch of salt. A computer has no idea what a pinch is. An algorithm has to be perfectly precise, step by step, so a computer can follow it to the letter without getting confused.
And for something to be considered a true algorithm, it actually has to check 5 boxes. First, it needs an input. Those are your ingredients. Second, it has to produce an output. That's your finished cake. Every single step has to be definite, crystal clear. And this is a big one. It has to eventually stop. It can't run forever. That's finiteness. And finally, each step has to be effective, which just means it's so basic that you could, in theory, do it yourself with just a pencil and paper.
So great, we have a set of instructions, it works, it follows all the rules, but how do we know if it's any good? If two people come up with two different recipes for the same cake, how do we figure out which one is best? Well, that brings us to the two main goals we're always chasing in algorithm design. Goal number one is non-negotiable. It absolutely must give the right answer, every time, for every possible input. But just being right isn't enough. It also has to be fast, and it can't be a resource hog, using up all the computer's power to get the job done.
So to measure that fast part, we use something called time complexity. Now this isn't about getting out a stopwatch and timing the code. It's more clever than that. It's about understanding how the running time grows as the problem you're solving gets bigger.
And to measure the resource hog part, we have space complexity. This is all about how much memory, or going back to our recipe, how much countertop space the algorithm needs to do its work. You know, a great recipe doesn't require you to use every single bowl and pan in your entire kitchen, right?
And here is the absolute key takeaway. What we really care about is how an algorithm performs when the problem gets massive. This idea, called asymptotic complexity, is what separates an algorithm that can sort a billion items from one that chokes on just 1,000. It's all about how it scales.
Now, to talk about this scaling and growth in a consistent way, computer scientists needed a common language. And that's exactly what they created. It's called Big O notation, and it's what we're jumping into next.
The best way to think about Big O is like a universal ruler for measuring code. It doesn't care if you have a supercomputer or a 10-year-old laptop. It doesn't care if the code is in Python or C++. Big O gives us a standard, objective way to compare the fundamental efficiency of two different solutions.
What Big O notation really does is describe the worst-case scenario. It tells us how an algorithm's runtime or memory usage will grow as the size of the input, which we just call n, gets bigger and bigger and bigger. It's not about measuring seconds, it's about measuring the rate of growth.
So here are a few of the most common ratings you'll see. O log n, or logarithmic, is the gold standard. It's incredibly fast. Think of looking up a name in a phone book. Then you have ON, or linear, which is pretty good. Double the input, you double the time. But then you get to ON squared, quadratic, and things start to get slow, fast. And at the bottom, you have things like O2 to the n exponential, which, well, they become impossible almost immediately.
So, why does all this matter? Why obsess over these letters and numbers? Because the difference between a good algorithm and a bad one isn't just a little bit. It's astronomical.
This table shows you everything you need to know. Just look at the rows and columns. When your input size, n, is tiny, like 8, all the numbers look pretty small. No big deal, right? Even at 16, things seem kind of manageable across the board. But just watch what happens when we double the input one more time, to just 32.
Our super efficient log-n algorithm takes only 5 steps. 5! But that inefficient 2 to the n algorithm? For that same tiny input of 32 items, it requires over 4 billion operations.
Let me put that in perspective for you. On a modern computer, the difference between 5 operations and 4 billion operations is the difference between something happening instantly and something taking minutes, hours? And as n gets just a little bit bigger, that gap becomes the difference between a millisecond and the age of the universe. That is the jaw-dropping power of a good algorithm.
And that really brings us to a final, pretty mind-blowing thought. The next huge breakthroughs in medicine, in climate science, in exploring our universe, they might not come from building faster computer chips. They might come from someone, somewhere, figuring out a better recipe. So the question to leave you with is this: what problems do we think are impossible today that are really just one great algorithm away from being solved?